Have you ever wondered about the nature of time and space? Let's dive into the world of Einstein's special relativity. This remarkable theory, first proposed by Albert Einstein in the early 20th century, begins with two fundamental postulates that might sound a bit counterintuitive, but they have been proven to hold true over countless experiments. The first postulate is the invariance of physical laws. This means that the laws of physics are the same for all observers in unaccelerated motion, regardless of their speed or direction. So, whether you're sitting still or moving at a steady speed, the laws of physics will look exactly the same to you. This is known as the principle of relativity. The second postulate is the constancy of the speed of light, denoted by c. This states that the speed of light in a vacuum is the same for all observers, no matter their state of motion or the motion of the source of light. Even if you're racing towards a beam of light at half its speed, it would still appear to be moving away from you at the full speed of light, a staggering 186,000 miles per second. These two postulates might seem simple, but they have profound implications. They force us to reconsider our understanding of space and time, leading to some astonishing predictions such as time dilation and length contraction, which we'll explore in the next scene. So, next time you look up at the stars, remember that the light you're seeing, traveling at a constant speed across the vast cosmos, is a testament to Einstein's revolutionary principles. These principles laid the foundation for a new understanding of the universe. So, what are the implications of these principles in our everyday life? Let's dive into the fascinating consequences and effects of special relativity. First up is time dilation. Picture this. As an object moves closer to the speed of light, time for that object slows down compared to a stationary observer. This is not just a theoretical concept, but a reality that even our GPS systems account for. Next, we have length contraction. This principle states that objects in motion appear shorter along the direction of motion. So, if we could somehow catch a ride on a beam of light, we would perceive a moving object as being shorter than it would appear if we were stationary. Quite a mind-bender, isn't it? Moving on, we encounter the concept of relativistic mass. This principle suggests that mass increases with velocity. Now, don't get any ideas about a speed-based weight loss plan. The changes are minuscule unless you're approaching the speed of light, which, let's face it, is beyond our current capabilities. Finally, we come to the famous equation E equals mach squared. This elegant equation tells us that energy is equivalent to mass times the speed of light squared. It's this principle that powers the sun through nuclear fusion, converting a small amount of mass into a huge amount of energy. These principles challenge our intuitive understanding of reality. They tell us that time and space are not as constant and unchangeable as our everyday experience would suggest. Instead, they can stretch and shrink, warp and curve in response to motion and energy. So, why does this matter? Well, it's because everything in our universe, from the smallest particle to the largest galaxy, follows these rules. Even though we don't notice these effects in our daily lives, they're continuously at play, shaping the fabric of our reality. These effects, while counterintuitive, are fundamental to the workings of our universe. You might be thinking, where do we see these effects in real life? Well, the principles of relativity aren't confined to the realm of theoretical physics. They have real-world applications that we often take for granted. Take particle accelerators, for instance. These are enormous machines that propel particles to near-light speeds. As these particles approach the speed of light, they gain relativistic mass. This means that their mass effectively increases. This is not due to an actual gain in matter, but rather a result of their high velocity. This increase in mass leads to an increase in their energy, as dictated by Einstein's famous formula E equals mc squared. This energy is then used in experiments that probe the very heart of matter itself. Without accounting for the principles of relativity, the behavior of these particles would be incomprehensible. So, particle accelerators serve as a tangible example of where we see the principles of relativity at work. Next, let's talk about something you probably use every day: GPS, or Global Positioning System. GPS satellites are constantly on the move, orbiting the Earth at high speeds. According to the theory of relativity, time for these fast-moving satellites slows down relative to a stationary observer on Earth. This is known as time dilation. Now, even a tiny discrepancy in time can lead to a significant error in calculating a location on Earth. To ensure accuracy, the GPS system has to correct for this time dilation effect. Without this crucial correction, your GPS device could be off by several kilometers. Imagine trying to navigate to your favorite coffee shop, only to end up in the middle of a river. So whether it's the cutting-edge research conducted in particle accelerators or the everyday utility of GPS navigation, the principles of relativity are at play. They are not just abstract concepts of high-level physics, but practical tools that shape our technology and our understanding of the universe. So, relativity is not just a theoretical concept, but an integral part of our technology. Now, let's take a leap into the world of general relativity and gravity. While special relativity deals with objects moving at constant speeds, general relativity steps up the game, bringing in acceleration and gravity. It all starts with a simple but profound idea known as the equivalence principle. Picture yourself in a windowless elevator. If it's accelerating upwards, you'd feel heavier, right? But how would you know if you're accelerating or if gravity has increased? The answer is you can't. Gravity is indistinguishable from acceleration. This is the equivalence principle. This concept opened the door to a brand new understanding of gravity. Einstein proposed that massive objects like planets and stars don't pull other objects towards them, but instead they distort the fabric of space-time around them. Imagine a rubber sheet stretched tight. If you place a heavy ball in the middle, it'll create a dip, a curve. Now, if you roll a smaller ball near it, the smaller ball will move towards the heavier one, not because it's being pulled, but because it's following the curve. This is the heart of general relativity, the idea that gravity is just the curvature of space-time caused by mass and energy. It's like objects moving on a trampoline. The heavy objects create dips, and the lighter ones move along these dips. It's not the objects pulling on each other, but the shape of the trampoline dictating their motion. This theory not only redefined gravity, but also made some fascinating predictions. It suggested that clocks in stronger gravitational fields would tick more slowly. It predicted that massive objects could bend the path of light, a phenomenon now known as gravitational lensing, and it also predicted the existence of gravitational waves, ripples in space-time caused by violent cosmic events. Einstein's general relativity gives us a new lens to view gravity, not as a force, but as a result of the curvature of space-time. Scene script. Have you ever dreamed about traveling through time? Let's see what Einstein's theories have to say about that. Imagine you're aboard a spaceship that can travel near the speed of light. According to the concept of time dilation, as your speed increases, time slows down for you relative to the rest of the universe. This means that for you, the traveler, less time would pass than for those you left behind on Earth. Upon your return, you would find that everyone else has aged more than you, making it seem as though you've traveled into the future. This is a form of time travel that is actually supported by Einstein's theory of special relativity. Beyond this, there are more speculative ideas. Cosmic strings, hypothetical one-dimensional defects in the fabric of the universe, and wormholes, shortcuts through space-time, have been proposed as potential paths for time travel. However, these concepts remain in the realm of theory and are yet to be substantiated by empirical evidence. Now, let's shift gears a bit and consider the fusion of space and time into a single entity, the space-time continuum. This unification, a cornerstone of Einstein's theory of general relativity, has profound implications for our understanding of the cosmos. It suggests that the universe isn't just expanding in space, but also in time, shaping our perception of the universe's evolution. General relativity has also made its mark in the field of astrophysics. Its predictions guide our understanding of celestial phenomena, such as the behavior of black holes and neutron stars. On a more practical level, we see the effects of special relativity in technologies like GPS, where corrections for the relativistic effects are essential for accurate navigation. While time travel remains a tantalizing possibility, the true power of relativity lies in its ability to shape our understanding of the cosmos.